Pick up your phone, now set it down. Simple actions performed thousands of times without thought. But pause for a moment and consider what just happened. Your hand applied force. Matter responded. Emotion changed according to rules that govern everything, from falling apples to collapsing stars. At the center of this everyday miracle sits a concept so fundamental that physics cannot function without it, yet so subtle that most people misunderstand it their entire lives. Mass, the word sounds simple enough. Heavy things have lots of it, light things have less. Massive objects are hard to move, but this intuition, while pointing in the right direction, misses the deeper reality. Mass is not heaviness. It is not weight. It is not even stuff packed into space, though it feels that way. Mass is something stranger and more profound. It is the universe's way of keeping score, a number that tells you how stubbornly matter resists change and how powerfully it shapes the fabric of reality itself. When you push that shopping cart through the store, when astronauts float weightless, yet still feel the effort of changing direction, when galaxies bend light, traveling across billions of years, the same principle is at work. Mass is speaking, and once you learn its language, the physical world begins making sense in ways that simple memorization never achieves. This is not about formulas to remember or facts to recite. This is about understanding why the universe behaves the way it does whenever anything tries to change. And that understanding starts not with equations, but with motion. Push an empty shopping cart, and it responds instantly, gliding forward with barely any effort. Load that same cart with groceries, and suddenly the same push accomplishes far less. The wheels have not changed. The floor beneath them has not changed. Your muscles applied the same force, yet the result is completely different. Something about the loaded cart makes it resist your effort to change its motion. That something is mass, and this resistance is the first and most important thing to understand about it. Mass measures how strongly matter opposes acceleration, not motion itself, but changes in motion. An object at rest resists beginning to move. An object already moving resists stopping or turning. Speed up, slow down, change direction. Every alteration of motion requires force, and mass determines how much force is needed to produce a given change. Double the mass, and you need double the force to achieve the same acceleration. Triple the mass, and you need triple the force. The relationship holds with mathematical precision across every scale we can measure. This principle appears everywhere once you know to look for it. When a car accelerates from a stoplight, the engine must overcome the inertia of the entire vehicle. The heavier the car, the more power required to reach the same speed in the same time. When a baseball pitcher throws a fastball, their arm must accelerate the mass of the ball from rest to high velocity. Throw a bowling ball instead, and the same arm motion produces a much slower result. Not because the throwing technique changed, but because greater mass requires greater force to achieve the same acceleration. Notice something crucial here. Mass does not care about speed. It cares about change. Two cars can travel side by side at 60 miles per hour, one a compact sedan and one a loaded truck. They move at the same velocity but attempt to stop them both, and the difference becomes obvious. The truck resists stopping more strongly because it has more mass. The velocity was identical. The resistance to changing that velocity was not. This distinction matters because it reveals what mass actually does. It does not measure motion. It measures how difficult motion is to change. Now bring gravity into the picture, and everyday experience starts blurring concepts together. On Earth, objects with more mass feel heavier. Drop a bowling ball and a tennis ball and both fall. But the bowling ball feels harder to hold up. This happens because gravity pulls on mass, More mass means stronger gravitational attraction, which we experience as weight. Since gravity is constantly present in daily life, our language treats mass and weight as interchangeable. Hold something heavy and you feel its mass through the effort of supporting its weight. Physics keeps these concepts distinct for good reason. Weight belongs to the relationship between an object and a gravitational field. Mass belongs to the object itself. Take that bowling ball to the moon and its weight drops to 1/6 of what it was on Earth. The moon's weaker gravity pulls less strongly, but the mass has not changed at all. Throw the ball on the moon, and your arm feels the same resistance to acceleration it would feel on Earth. Push it across a smooth surface, and it resists exactly as it did before. Mass is intrinsic, weight is contextual. This separation becomes especially clear in situations where gravity is absent or negligible. Astronauts aboard the International Space Station float freely, experiencing what is commonly called weightlessness. They have no weight because they are in continuous freefall, but they are not massless. Push an astronaut floating in the cabin and they resist the push just as they would on the ground. Stop pushing and they continue drifting at constant velocity until something else interferes. Their mass remains unchanged even though their weight has effectively vanished. The resistance to acceleration persists regardless of gravitational circumstances. This reveals something fundamental about the nature of mass. It is not about holding things down or pulling them toward Earth. It is about resistance to change regardless of where that change is attempted. On Earth, in orbit, on the moon, or in the empty depths of space far from any gravitational influence. Mass behaves the same way. It opposes acceleration with a strength that depends only on how much mass is present. Here is where physics discovered something extraordinary. The quantity that determines how strongly gravity pulls on an object turns out to be exactly the same quantity that determines how strongly that object resists acceleration. This is not approximately true or true with some adjustment factor. It is exactly true, verified by experiments with astonishing precision. Drop a feather and a hammer in a vacuum where air resistance is eliminated, and they fall at identical rates despite having very different masses. Why? Because the greater mass of the hammer makes it resist acceleration more strongly, but it also makes gravity pull on it more strongly, and these two effects cancel exactly. This equivalence between gravitational mass and inertial mass is not obvious. Nothing in principle requires them to be the same. You could imagine a universe where the mass that resists acceleration is different from the mass that responds to gravity, but experimental tests show they match to better than 1 part in a trillion. No difference has ever been detected. This perfect agreement points to something deeper about how mass works, something that goes beyond simple resistance to forces. The implications of this equivalence are profound. It means that mass connects two apparently different aspects of the physical world: how objects respond to forces and how they create and respond to gravity. These are not separate properties that happen to have similar values. They are the same property appearing in different contexts. Mass sets the scale for inertia and simultaneously sets the scale for gravitational interaction. One number plays both roles without adjustment. This already suggests that mass is more fundamental than it first appeared. It is not just a measure of how much stuff an object contains. It is a measure of how that object participates in the physical laws governing motion and gravity. The resistance you feel when pushing a loaded cart and the weight you feel when holding it up against gravity both arise from the same underlying property. Mass has revealed itself as a bridge between different phenomena. unifying concepts that everyday experience keeps separate. Understanding this prepares the ground for a deeper question. If mass measures resistance to acceleration and simultaneously determines gravitational influence, what exactly is it resisting? What makes matter push back when forces try to change its motion? The answer turns out to involve not just matter itself, but the structure of space and time. Up to now, mass has sounded like a property objects carry with them, something internal, localized, and self-contained. But mass does more than determine how objects respond to forces. It participates in shaping the structure of the universe itself. To see this requires shifting perspective from objects in space to the nature of space itself. Imagine a universe without mass, a purely empty arena where space and time form a simple, uniform grid. In such a universe, straight lines would remain straight forever. The clocks placed anywhere would tick at identical rates. An object set in motion would continue in a perfectly straight path at constant speed unless acted upon by some external force. Space would provide a neutral stage, and time would flow uniformly for all observers. This is the classical picture, the one that intuition builds from everyday experience. Introduce mass, and this picture no longer holds. Mass does not simply respond to the stage of space and time. It affects the stage itself. This is where modern physics departs most dramatically from everyday intuition. Space and time are not separate, fixed backgrounds where events occur. They are joined into a single entity called spacetime. And this entity responds to the presence of mass and energy. Mass tells spacetime how to curve, and spacetime tells matter how to move. This sounds abstract, so start with a concrete example. Place two identical clocks side by side and synchronize them. Now lift one clock higher while keeping the other on the ground. Let both run for a while, then bring them back together. The clocks no longer agree. The one that was higher ran slightly faster than the one left below. The difference is tiny, measurable only with extremely precise instruments, but it is real and predictable. Time itself runs at different rates depending on the proximity to mass. This is not a defect in the clocks or an error in measurement. Time genuinely passes at different rates in different locations near massive objects. A clock on the ground floor of a building ticks more slowly than a clock on the top floor. A clock at sea level runs more slowly than a clock on a mountaintop. The effect is small because Earth's mass, while large by human standards, is not enormous compared to the scale required to make gravitational time dilation dramatic. But it exists, it is measurable, and GPS satellites must account for it constantly to maintain accuracy. The same phenomenon affects distance. Space-time near massive objects is not flat and uniform. Paths that would be straight in empty space become curved near mass. Light, which has no mass of its own and travels in the straightest possible paths through space-time, visibly bends when passing near massive objects like the sun. Nothing pushes the light sideways. No force deflects it. The light simply follows the geometry of space-time, and that geometry is curved by the sun's mass. This is what gravity actually is. Rather than thinking of gravity as a force reaching across empty space to pull objects together, modern physics understands it as the result of mass curving space-time. Objects then move according to that curved geometry. A planet orbiting a star is not being pulled by an invisible tether. It is following the straightest possible path through the curved space-time created by the star's mass. What looks like circular orbital motion from outside is actually straight-line motion through curved geometry. This explains an old mystery. Why do all objects fall at the same rate, regardless of their mass? Assuming other effects like air resistance are eliminated, Galileo demonstrated this principle centuries ago, but the reason remained unclear within the framework of forces acting on objects. The answer becomes obvious once you understand that falling objects are responding to space-time geometry rather than to a force. The curved space-time near Earth affects all objects the same way, regardless of their individual mass. A feather and a hammer follow the same curved paths because the paths are properties of space-time, not of the objects traveling through it. Mass shapes space-time, and objects respond to space-time. This is the central insight of general relativity, and it transforms mass from a simple property into a fundamental participant in the structure of reality. The resistance to acceleration that defines inertial mass and the gravitational attraction that defines gravitational mass are two aspects of the same thing: how matter affects and responds to space-time geometry. Now pause and connect this back to the idea of resistance. An object with mass resists changes in motion. Space-time with mass resists being flat and uniform. In both cases, mass introduces structure and constraint. It makes the universe less flexible, more rigid, more resistant to being different than it currently is. The loaded shopping cart resists your push. Space-time near Earth resists being flat. These are not separate phenomena, they are different manifestations of what mass does. This brings up an important detail that causes frequent confusion. Mass is not the same thing as energy, but they are closely related. Energy contributes to space-time curvature in exactly the same way mass does. Heat, electromagnetic radiation, even the kinetic energy of moving objects, all of these affect space-time geometry. Mass tends to dominate in everyday situations because it represents concentrated energy in a relatively stable form. But the principle is more general. Energy in any form participates in shaping space-time. That famous equation connecting mass and energy is not primarily about nuclear reactions or explosions. Though it applies there, it is a statement that mass is one form that energy can take, and that any form of energy contributes to space-time curvature. Rest mass, the mass an object has when sitting still, corresponds to a certain amount of energy. Add energy to a system, and you effectively add mass. Confine energy tightly enough, and it behaves exactly like mass, resisting acceleration and curving space-time. This reveals why light, despite having no rest mass, still feels and creates gravitational effects. Light carries energy and momentum. That energy contributes to space-time curvature, and the light itself follows the curved paths created by other masses. Black holes can trap light not because they exert a force on massless photons, but because space-time near black holes is curved so extremely that even light's straight-line paths cannot escape. The geometry allows no outward routes. At this stage, it helps to let go of the idea that space-time is a thing sitting underneath everything else. Space-time behaves more like a network of relationships, how distances are measured, how durations pass between events, how paths connect one point to another. Mass influences those relationships directly. The influence is not optional or switchable. Any amount of mass, no matter how small, contributes to space-time geometry. The effects become noticeable only when mass is large or concentrated, but the principle applies universally. What began as resistance to acceleration has expanded into something larger. Mass measures how strongly matter participates in the geometric structure of reality. It tells spacetime how to curve, setting the rules for how objects move and how forces propagate. Once you see this connection, mass stops being merely a property of objects and becomes a fundamental component of how the universe is organized. Every massive object, from electrons to galaxy clusters, contributes its small or large share to the overall geometry of spacetime, and that geometry, in turn, governs how everything moves and interacts. Once mass is understood as something that shapes spacetime itself, another question becomes unavoidable. Where does mass come from? Up to this point, mass has appeared as a given, a fundamental quantity that objects simply possess, but physics seeks mechanisms, not just descriptions. The answer to this question reveals something surprising about the nature of matter itself. Consider a proton, one of the particles that make up atomic nuclei and therefore most of ordinary matter. Protons have mass, approximately 2,000 times the mass of an electron. You might reasonably assume this mass comes from the particles inside the proton. After all, protons are not fundamental. They are composed of smaller particles called quarks, bound together by the strong nuclear force. Add up the masses of those quarks and you should get the mass of the proton, right? Wrong. If you sum the intrinsic masses of the three quarks inside a proton, you account for only about 1% of the proton's total mass. The remaining 99% comes from somewhere else entirely. It comes from energy. The quarks inside a proton move at tremendous speeds, and they interact through forces so powerful that the energy involved dwarfs the quarks' rest masses. According to the relationship between mass and energy, this confined energy contributes to the proton's mass. Most of what you call matter is actually energy held in place by interactions. This means that mass, at least for ordinary matter, is not primarily about tiny particles having intrinsic heaviness. It is about energy being bound and constrained in ways that create resistance to acceleration. The mass of protons and neutrons comes mostly from the dynamic energy of quarks and gluons interacting at enormous intensity within an incredibly small volume. The mass of atoms comes from the mass of protons and neutrons in the nucleus, plus a small contribution from electrons, plus binding energy that holds everything together. Scale this up, and the mass of everyday objects, tables, cars, planets, stars, traces back to energy confined by interactions rather than to some fundamental substance called mass stuff. This explains why mass is not evenly distributed through matter like butter through bread. It concentrates where energy is most tightly bound. Nuclear matter has high mass density because strong nuclear interactions trap enormous energy in tiny volumes, expand matter into gas, and the mass density drops, not because mass disappears, but because the same amount of mass occupies more space. Heat something up and its mass increases slightly because you have added energy. The increase is far too small to notice in daily life, but the principle applies. More energy means more mass. Now this raises a question. If most mass comes from confined energy, where does the intrinsic mass of particles, like quarks and electrons, come from? Why do they resist acceleration even when alone and at rest? Here the picture shifts to fields. Particles do not exist in isolation. They exist embedded in fields that permeate all of space. One particular field, the Higgs field, plays a special role in giving certain particles their rest. Mass. The mechanism works through interaction. The particles moving through the Higgs field interact with it constantly, and this interaction creates resistance to acceleration. And the stronger a particle's interaction with the Higgs field, the more mass it exhibits. Particles with no interaction, like photons, have no rest mass, and always travel at the maximum speed allowed by spacetime. Particles with strong interaction, like the W and Z bosons that mediate the weak nuclear force, have substantial mass and cannot travel anywhere near light speed. This means that even intrinsic mass, the mass particles have when sitting still, emerges from interaction rather than being a standalone property. Mass at every level is relational, expressing how particles and energy engage with fields and forces. It is not something objects carry in isolation. It is how they participate in the structure of physical law. Remove all fields and interactions, and the concept of mass would become meaningless. This relational nature clarifies why mass behaves consistently across different contexts. In mechanics, mass determines how force produces acceleration. In gravity, mass determines how objects influence space-time geometry. In particle physics, mass reflects interaction strengths with underlying fields. In relativity, mass contributes to the energy momentum content that curves spacetime. These are not different types of mass requiring different explanations. They are the same property appearing in different phenomena because mass fundamentally describes how matter and energy participate in physical processes. Understanding this also explains phenomena that otherwise seem puzzling. Consider motion at speeds approaching light speed. Push an object and it accelerates, push harder and it accelerates more. But as the object's speed increases, the same force produces smaller and smaller changes in velocity. Eventually, no amount of force can push the object past the speed of light. This is sometimes described as the object gaining mass, but that description misleads. The object's rest mass has not changed. What has changed is how spacetime constrains motion at high velocities. The resistance to further acceleration increases because spacetime itself imposes limits on how motion can change. Mass and spacetime work together at fundamental levels. Mass tells spacetime how to curve. Curved spacetime constrains how objects move. At low speeds, this manifests as simple inertia. At high speeds, it becomes a geometric limit. At all speeds, it reflects the same underlying principle. Matter and quite spacetime form an integrated system where mass quantifies participation and influence. Now bring this understanding back across scales. At microscopic scales, mass arises from particle interactions with fields and from energy confined by forces. At human scales, mass governs how objects respond to pushes and pulls, determining the effort needed to change motion. At astronomical scales, mass shapes spacetime profoundly enough to bend light, trap energy in black holes, and determine how galaxies move. The same concept applies everywhere. Only the language and the relevant equations change. This universality is what makes mass such a powerful and reliable idea. It appears in classical mechanics, thermodynamics, quantum field theory, and general relativity without shifting its fundamental role. The mathematics looks different in each framework, but the physical meaning persists. Mass always measures resistance to change and always participates in determining spacetime structure. This consistency across theories is not coincidence. It reflects the fact that mass describes something real, fundamental, about how the universe works. So when someone truly understands mass in physics, they have learned more than a definition. They have learned how physicists think about change, why motion responds the way it does, why gravity behaves universally, and why energy cannot be rearranged without consequences. Mass becomes a practical tool for reasoning. It explains why heavy objects require more force to accelerate than light ones, why astronauts float yet still resist pushes, why stars bend the paths of light, and why most ordinary matter owes its mass to energy bound by interactions rather than to the intrinsic properties of fundamental particles acting alone. Once mass is understood this way, it stops generating confusion. It becomes predictable and explainable without memorizing definitions or relying on vague analogies. Mass is how physics tracks resistance to changes in motion and influence on spacetime geometry using a single quantity that there works everywhere it applies. And that is why mass remains one of the central concepts in physics, not because it is mysterious or complicated, but because it is reliable, universal, and deeply connected to how reality is structured at every level we can test and observe.